Now, let me start by first saying, for me, it's really great to be here finally for the first time as a speaker at the MLSS myself. First time I've been to MLSS was in 2003 here in Tübingen, and well, it was one of the ways of how I got attracted to actually being at this place now for nearly 10 years by now. Always regularly doing research. I hope the same opportunity will come to many of you. So let me start. And Root has really posed a challenge on me. I'm supposed to give both a breadth and a depth overview over reinforcement learning. And as I only had half a day in my schedule, which I could free, well, that boiled down to reinforcement learning in 90 minutes. Now for you guys, this is going to be a pretty big change. Up to now, all the lectures you saw were pretty much about you take a data set, usually a very static one, and then you use, well, you learned some model onto it, whether it was a complex network, a deep network, lots of things. Now we're going to move away from this. Since, for example, for robotics or for any kind of autonomous intelligent system, supervised learning is usually not enough. Sure, you can learn good models of the body, they can be useful. You can learn from demonstrations, but demonstrations are usually imperfect. You can't demonstrate everything. So what we really need in any system that acts is, well, the capability of exploring, as for this robot. And usually our teacher only tells us good robot, bad robot, like this professor. So what really active machine learning system, intelligent system, autonomous systems need are that they need to explore by trial and error. And that, of course, also means that, well, your feedback is really a reward. Quick note, I'll always use reward because I like Rich Sutton, but there are large communities which instead say cost all the time, which is just negative reward, and they use a minimum where we use a maximum. Consider that a subtlety. So what we're going to look at today is how we can derive optimal actions, or actually how to derive recipes for optimal actions that maximize the long-term reward. We're going to look at 3 different roads towards this. We're going to start with a very, very classical component. When you look at from normally in control, people for several hundred years have taken physical models they made up by hand and then computed a value function from this policy. This part is actually just called optimal control. Now we'll use it with the additional step of first learning a model, then bringing in optimal control, and by that actually changing our data set. Now that is the very classical way of how you could start this. You're just generalizing the human using a machine learning approach. And then we are going to go in the second part of the lecture. We are going to make it simpler. We're actually taking the approximation step away from going from the data to the model. We'll actually do the approximation step from the data to this thing called the value function. Consider it at the moment like a magic function telling you how good every state or how every state action pairs. And then we're going to realize that even this value function maybe is too complicated. We're going to look at only learning the policy directly approximated data. All of these times, the interaction is of course. Let's start with the optimal control perspective. And I'll pose you in a wonderful scenario. Tomorrow morning, you wake up and you have won a best paper award in Madrid about a paper you had long forgotten, and you have to suddenly, would have to fly to Madrid, collect. Okay, go to the internet, you directly see all the connections from Stuttgart. There's obviously no direct connection as usual. And you have to fly via London, Paris, or Rome in order to get there. And then you look at these flights and the costs, and you realize, well, they're quite differently priced. Can be 95 euros, can be just 5 euros if you take Ryanair, which I wouldn't recommend. So how would you actually solve this problem? Well, it turns out that there have been a series of people addressing this problem in different contexts, but there was only one guy who came up with a general principle for that. That's this fine Mr. Bellman, who had really an outstanding work, and he called this general recipe the principle of optimality. So in the principle of optimality states that an optimal sequence of controls in a multi-stage optimization problem has the property that whatever the initial state and controls are, the remaining controls must constitute optimal sequence of decisions for the remaining problem with the stage and state resulting from the previous controls considered as a transition. Now that's a lot of text. What it basically says is, break your problem down for the last day where you die, solve this one first, then look at the day before you die, solve it then, and then go back all the way until you're born. In much simpler words. So break down your problem. And in fact, dynamic programming, which resulted from that, is today a standard algorithm design technique, which you usually learn in your graduate algorithm school. Nevertheless, let's start right here. And let's start with the day, your last day in your life, the day of receiving this best paper award in Madrid. And obviously, if on this last day, on the day of the paper, of the day you die, or where you receive the best paper award, well, if you're there in Madrid already, well, in that case, go pick up the 1,000 euros. If you're in Tübingen instead, well, you may want to stay in Tübingen and attend one of these nice lectures. I don't know, in London, you may want to throw some eggs at Theresa May. And, well, I don't know what you would do in Paris. Maybe look at the Eiffel Tower. Oh, sorry, Paris is far. Look at the Eiffel Tower, and in Rome at the Colosseum. But let's say you had 2 days to live. So the day before you die. Now, if you're in machine learning summer school in Tübingen again, well, you want to stay here for one more day. And instead, since you're not going to make it, as there's no direct flight, you're not going to make it to the conference. And, well, you're not going to pick up the award. But from all of the other locations, you realize there is a flight, and you have to subtract the flight cost in order to get Madrid. So you actually have an optimal action for all of these states. Okay, let's go further back. Now, let's say you had 2 days to live. Now, for 2 days to live, it actually makes sense. Well, let's skip these lectures in Tübingen and rather pick up the $1,000, the best paper award. It's, after all, something too. Maybe not quite as good as hearing Bernhard speak, but, well, you directly have, again, now an optimal policy, which in this case has actually only one action change. Now, if you, one action change. If you let this go for sufficiently long, you realize that these arrows no longer change. It also means you have converged. Your lifetime is suddenly long enough that your policy will no longer change. Now, that's actually, well, actually quite an important aspect of such problems, since, well, that means that you don't always need to go all the way back until the day where you get born, but you could probably take something big. Alrighty, what I've described to you at this stage is called the Markov decision process. Now, a Markov decision process generically has a system which is in a state as part of a state space, and most people up to very recently who worked in reinforcement learning considered these things to be discrete, because for discrete we can do many things, and that's why we in reinforcement learning up to 5 years ago always heard, oh, you do reinforcement learning, oh, you do grid wells. And no, I've never done grid wells, but it's actually a very recent thing that the whole community now moved away towards more interesting topics, and they're no longer just about grid. But you could think of these as any kind of set, basically. Now you have an action space, which again is a set of actions. And here discrete is obviously much easier because a max operator over a discrete set is much easier than over a very complex text space. Then you have transition dynamics, since, well, when you fly with Ryanair, well, probably this graph is not going to be enough, but instead you will miss a flight, or even worse, if you fly United, you get dragged out of it. And you end up, well, not making your best paper award. So the probability of actually reaching the next state is quite important. Believe me, last week I flew United and I didn't reach my goal, and it was the European Parliament. They weren't that happy. And then you have these rewards, which are already written here as the number, well, as these numerical scores here in terms of money. Now, in many sciences, like in the neurosciences, in behavioral sciences, and psychology, people actually care a lot about figuring out what rewards humans actually have. And this is has become a complete science by itself where reinforcement learning is applied. Now, most importantly, your state should be a sufficient statistic of your complete past state and actions. Now, that, of course, means that you can boil down this long conditional distribution to just a conditional distribution conditioned onto your last state and your last action. That's a very, very important part about your model. This, of course, can mean that if you really want to do the most general case, that your state can grow, that your state can be some continuously growing high-dimensional vectors. But, of course, in most of reinforcement learning, because reinforcement learning is hard by itself, people keep the dimensionality. So now let's look at the system. And the system at every stage has a policy, which is a distribution over actions given the state and, well, sometimes some parameters for learning it. Then it takes an action, puts it into the system, receives the next state, receives the result. And what we want to accomplish is we want to maximize the expected return for the expectation over being over a start state distribution, the model, and the policy. And we have introduced this little gamma here. Why do we have this gamma? Well, we want to bias our system towards respecting the immediate reward a bit more than the long-term reward. You can think of gamma as an interest rate. If you have to always pay a certain percentage to the bank or to the state in terms of taxes, well, obviously, you're going to work less hard, which is well known in economics. You can, in the case where we have a finite horizon, where this t actually ends, we could actually let this discount rate go to 1, but it obviously helps to have it slightly faster, slightly lower. Now let's take Bellman's recipe, and it's actually only a very small change. Now you start again at the day where we die. So at time equals t, we insert the optimal reward, or the reward of the final stage, into the value function for initialization. And then we basically use countdown from capital T to 1, so the day where we get born. And before, we were just looking up always the value of the next state. Now, in this case, we replace this by computing an expectation. When you put together the reward plus all the discounted future rewards, we call this a state action value. It's literally the same as what we had before, just that we had a deterministic system here. And then when we compute the arrows, which we had before, what we do is we just do the max operator over this function. The very end, when we have gone to the very first day, the day where we were born, well, we can extract the optimal policy, return this to our system, which can then try it out. Piece of cake? Everybody knows this? Or should I slow down? Okay. Seems I'm doing an okay speed. Okay. Now, this what if, this is a what if we would live infinitely long? If we live infinitely long, we obviously cannot count down to 1, but nicely, these equations converge, and we actually get a fixed point equation, which tells us the value of every state in which we can encounter in our life, and we know exactly, well, what would be the optimal action. We could do this either based on the Q or on the V function. And we could even draw this. Like, look here. Here you have a typical grid world. I should probably not have said that I never do them, but for illustration, they're quite useful. Here are little puddles, and if you fall into them, that is about as nice as falling into the Neckar River in Tübingen. You feel fairly cold afterwards, or maybe today refreshed. That's maybe a different story. You really want to get rather to the beer at the beer garden. Now, obviously, being too close to the river here, before you fall in, and you actually have a long way because you have to go all the way. And this basically shows, as a map, how valuable every state is. Now, beware how good things are when you're living infinitely long depends a lot on this discount factor. And if you move this discount factor to a very low number, you converge very fast and you're doing a very good job. But obviously you're going to be very short-sighted. If you make it very big, well, in that case you're going to be very long-sighted, but you may never converge. This is kind of like the decision of whether you want to smoke or not in your life. If you just look at the short-term reward, well, you feel good because of the nicotine. If you put up the discount factors so that it covers 10 years, well, then you may actually think about losing fitness and dying due to cancer, which obviously gives you two very different. And I want to quickly point out there is one alternative way, instead of always backing up and doing the max operator. If your max is costly, then you much rather want to first compute the Q function for a fixed policy and only subsequently improve the policy. So you would actually only compute the expectations all the time, but not update the B function at all. That would give you, well, this would be basically the same algorithm as before. It would just do a policy evaluation, and then after you've lived one infinite only long life, you can do policy. Good. Yes, sir. Okay. And very, very simple. The Q function is a function of state and action. It always tells you well, how much long-term reward you will receive on average if you take action A, state S. The V function tells you, assuming you have a policy, let's say here even an optimal policy, when you now always act according to this policy, that is how much you will receive in this state, not knowing actually what the action is. Now for the deterministic optimal policy, we don't really care because there is one action only for every state. But for a stochastic policy or a problem where we cannot observe all the information, it may actually be beneficial to have a stochastic. And you will see later how this, how stochastic policies, right? They become much more useful when you're dealing with value function policies. Then while in optimal control, they don't make that much sense. Okay. So now I want to flash at you, just to make you totally realize this, that we actually are not at all doing something new now in reinforcement learning, that we've discovered higher dimensional vector spaces as state action spaces, nor that there is actually way more than the discrete stuff. In robotics, or more precisely, robot control, especially in optimal control, we've been knowing this forever. The most famous example of that are linear quadratic Gaussian systems. They come actually with a fairly cool story because Bellman believed this would be doable, but Kalman came up with it because he saw that the Kalman filter is basically also just an optimal control problem, relative to the full estimation, and he published it, and Bellman was so unhappy with his PhD student who was supposed to discover that, he actually threw him out of a window. I don't know how badly the guy was hurt. Don't worry, Bellman is no longer active as supervisor. He died in '84 or something. So, no more PhD students die. No, I'm not sure that they died. Most importantly, in this case, we have a conditional distribution over a continuous state, given the past continuous state and action. And here I on purpose took the control notation. They love X and U instead of S and A. And if you do this with Gaussian noise and the linear mean and a little drift term, as well as a quadratic reward, you actually can solve this. And here I want to show you actually one of the first robotics examples. So in this case, you see a robot which estimates the linear model of the dynamics of this pole and of its hand in this particular scenario of staying close to an equilibrium point. And you see basically that it generates, just by trial and error, the right kind of data so that the optimal control policy will arrange. By simply plugging in now continuous spaces, we can actually already solve quite a problem. I don't know how with you guys, but I'm pretty sure. Oh, So this thing I can't do pole balancing. I need a very, very long stick in order to do this. It took me years to get that far. And this thing can do it forever. Now let's look at a slightly simpler problem. Let's say I just had a motor, and this motor wasn't strong enough, and I wanted to get this rotated up. It's a very typical problem, happens to the space shuttles all the time, and it's actually one of the cool skills you need in order to be an astronaut. If you can bring an arm up and inject energy so that you can then pick out a satellite back out of the space shuttle, but if it's flying. So it's actually quite a useful pumping up problem. In reinforcement learning, they also love to call this the mountain car problem and have a bit more esoteric version out of it, because Rich Sutton once had to bring his car out of it. It's actually mathematically equivalent. And when you look at this swing up problem, and the swing up problem the swing up problem you can nicely put discretize, because your state space is just two-dimensional. So you take something of, I think it was 280 billion states in order to get this beautiful, pretty picture of the value. Now you of course realize around the equilibrium point here, we can do a really good job with the LQR in some region. But actually here, just go a little bit too far, we actually would have to go all the way around again in order to bring the line, in order to get back to the equilibrium point. So it's actually, here's something fundamentally wrong if you were just doing equilibrium. So quite clearly, LQR doesn't really suffice, because the value function, in most cases, is highly nonlinear and for sure not quadratic. You can usually not discretize it because your state usually has more than 5, 6 dimensions, so you can never build the table. And in the end, well, and in addition, it is quite discontinuous here. So you actually even have a problem when you're using an off-the-shelf machine learning, supervised learning method in order to acquire such a. Now, what would you do if you were still an optimal controls person? But Chris Atkinson, already in the late 1980s, when the neural networks were hip the last time, came up with actually a pretty cool solution. He decided he will just start to create optimal trajectories, and he will always sample points where he will get to the optimal trajectories. And you saw that they actually behave fairly regularly. So basically, if we know where we want to start, then we may just want to approximate our solution locally around the trajectory. That sounds like magic. No, it's not magic. Luckily not. You just have to think of your system as a function where you use a Taylor approximation, and you can then locally linearize around either an equilibrium point or an equilibrium trajectory. However, there's a catch, the really, really important part. You need to know the optimal trajectory in order to get the optimal controls, and the optimal trajectory actually has to be an equilibrium point of a continuous system. And since you cannot linearize a system, what some people always tend to say, you can only linearize a system around an equilibrium point. That's actually a key part. Whether that's a stable or unstable equilibrium point is a different story. But it needs to be. And that way, you could get your linear system just indexed by time, and you could get your rewards, in this case, as a quadratic reward for the Hessian. That's pretty cool. And then we plug this into our optimal control case, and we could go backwards from a final state, compute the optimal trajectory, but compute optimal controls along a trajectory. But for that, we obviously have to know the trajectory. So in the next step, in order to improve, you need to first run a simulator from our desired starting point, propagate all the way to the goal, and then again go backwards. And people do this online. When this is done online, it's called model predictive control. But it's actually, when you do it, fairly fragile. Nevertheless, it's still becoming, well, up to very recently, this is still considered a fancy, up to today, it's considered a fancy method, even being reinvented all the time. Emo Todorov and Yuval Tassak call it ILQG or ILQR, but in reality, the methods for this differential part have all been published under the name differential dynamic programming as early as the 1960s by people like Dyer, Max Planck, Reynolds, and others. Now, the first person to really use this massively and actually use to complete the differential dynamic programming was Chris Atkinson. This is when he still was young. And you basically see him do this swing up, which I just did here, but he did it as a Karpro swing up, so there is no motor at this end effector, but it really just moves due to the movement of the rod. And he gives it first now a cost function where it has to pump in little energy, and then basically he gives it a cost function where it actually can even do less actions, so it has to pump in more energy in order to get up both. Now I should add, there was a little bit touchy. Chris actually managed to always get nicely trajectories which would swing the pendulum up, but for the stabilization, he actually had to fudge a lot of reward terms in order to make it. Why was this? Well, it was because the neural network which he used for approximating the reward function and the model had sufficiently many little problems that the reward function was never good enough until he really re-engineered it to work very well with the neural network. But obviously, this was 1980s. This was pioneering work. Okay. So, cool. Let's go home. All solved? Nah, you guys aren't that lucky. Unfortunately, this is a huge catch. We can only do discrete systems in general. Since, well, it's easy. You just sum over the world. And, well, you have no integrals or anything. But unfortunately, the world is not discrete. And we all know what Bellman screamed out when he tried to automate hospitals with dynamic programming. He screamed out, oh, there is this curse of dimensionality that whenever you move to more than a few dimensions, when you're moving with the dimensions, the number of little table entries grows exponentially. And so you're guaranteed to find a dimension where your algorithm doesn't work anymore. For LQR, well, the world is not linear, and your rewards are usually not quadratic. And again, along a trajectory, optimal trajectory, you first have to find the optimal trajectory, and you're absolutely not guaranteed that you will be finding it. In all other cases, you have to actually do more approximate measures. So let's have a look here. And that basically brings us to the, well, also the late 1980s, where Rich Sutton and Andy Bartow really brought value function methods to life. I should add that there was one PhD student at MIT, Paul Verbus, who actually came up separately with them, just get this bad luck of being in the lab of Marvin Minsky, and that was politically really the wrong time to come up with the learning method. Since that was before the second revival of the neural networks, and Marvin Minsky was the guy who built them the first time. So, we're going to start with the value function methods, and really to motivate it, we can use Chris Atkinson again, who you can see here again. He looks like Santa Claus. And he just gave a talk right after the American election, which I found fantastic. He basically states, Clinton was model-based, using strong predictive models, very accurate ones, and who would vote, how they would vote, and really tuned the hell out of the system. Well, that fine yellow wig didn't use any models. He just acted out of his gut. So quite clearly, it would be nice to have just good gut feeling and ignore all of the models. For me personally, it has actually been devastating at times when I try to learn models and use models actively in reinforcement learning. Since inherently, you're learning an optimal system which wants to take optimal actions. So if it has a bad model and it realizes that it can exploit the model, it will, of course, do so. So I had just arrived here at Max Planck in 2007, and Bernard had bought me this pretty new robot arm, which we still have. You may have seen it play table tennis at points. We were just totally happy getting started. And I learned a model and then learned optimal controller for it. And I was computed optimal controller for it. I was really, really happy. It looked at simulation fantastic. And I ran it on the rear robot, and the rear robot made boing. It broke, and I had to go to Bernard and say, please, can you now also pay for the repair? It wasn't a very good first impression, let's put it this way. Now, what had happened? What actually had happened is that I had a really precise model. Well, actually, in normalized mean squared error below 0.5%. So you could say, for all practical purposes, this should be a perfect model. We humans never have such an accurate model. But what actually had happened in there? Well, at times, the model had the wrong slope. Now, what does the wrong slope mean in a dynamical system? Well, in a mechanical system, it means you may have negative friction. So you can actually, instead of friction taking away energy, friction gives you energy. And if your optimal system decides, hey, I want to use this energy, it will directly start to oscillate and bang, go into a crazy state and break itself. So a tiny model error can completely break what you're doing. So with other words, well, that is quite a downside. And already only for we can only really make optimal control work if we're very moderately nonlinear or very, very low dimensional. So what people then proposed is, well, let's screw this model business. And Rich Sutton, today he's actually model friendly, but back in the days he was dogmatic about this. He said, we humans don't have models at all. We use just a value function, just our gut feeling. We're all like Donald Trump. Luckily not, but it was a major insight nevertheless, that since value function alone help us out. So let's now, for this case, move to the infinite horizon. So we now let t go to infinity. So we live infinitely long, since only in that case we have this inherent value function, which can actually be computed for all states without including time into our equations. To do this, we also have to assume that we have taxation, since otherwise we could, this whole function could blow up if we always get a positive reward here. So we have taxation or interest rate, or however you like. So it's actually a major change we have in here, or major limitation. And just again, remember, gamma trades off smoking versus non-smoking, meaning long versus immediate. Now, you've already seen the Bellman equation. In this case, we do one tiny change. Instead of having the max operator, we actually now just take a stochastic policy, meaning any distribution over action given the state. And this gives us, again, a value of every state and a value of every state action pair, both Q function and function. In classical reinforcement learning, we would actually now again take the data set. We would directly take the data set and not compute a model, but really let our samples speak. And let's start simple. We're going to start with a tabular function. What do we need to do? Well, what we want to do is we want to estimate first the V function, and then we do one step ahead. We predict for our next state, which we will get this reward plus this we will take this future prediction. This is going to be our prediction. Now that of course also means that we can use this one-step prediction in order to compute an error. This error is called the temporal difference error. And it's actually a little bit magical. Still up to today, there's some mysteries around it. That if you want to read some really cool paper even from 2003, look for Schoknecht-Nips 2003. It's actually surprising how little we understand the value function up to today. Now, if you bring it into this tabular representation, you would of course say, my next value should be what I had previously stored, plus, well, this correction, meaning a small learning rate alpha, times this little error. And then you can do something which Tommy Jakola at MIT did. He reordered these terms, and he realized Well, that, of course, would be the same as averaging with the 1 minus alpha, taking the geometric average between the past value and alpha times the new value. And Jakola could actually prove that for any discrete problem, this update rule is guaranteed to converge the optimal solution. Unfortunately, you should highlight that there are two conditions. A, it needs to be a discrete problem, and B, you need to visit every state action pair in itself. Small downtake when you're dealing with a real system. Now, the TD error actually comes with a good intuition. Intuition is basically, well, if you have an error, that obviously means you're comparing our prediction with what actually happened. And if our prediction is too high, well, then we should obviously decrease the value. If our prediction is too low, well, in that case, we actually should increase that value. Oh, but the other way around. I didn't put on the slides at this point. Very soon. Okay, this gives us a very simple algorithm. We get born, we initialize our value function with all zeros, since we know nothing about the world. And then we take our policy, and from our policy, which we just believe we've been born with, so we don't learn anything. We're not like a human, we don't learn how to walk. We're like a horse, we get born and we directly know how to walk. And now we compute the state, we compute our optimal action, we observe a reward, observe a next thing. And, well, we can compute the TD error and update our value function until we finally converge. Beautifully, right? We can get a value function that way. That's a sample-based version of just evaluating our policy. But obviously, there's one important part missing. What's missing, guys? Okay. Well, we're learning the value function, but we are not learning our actions. So what we actually need is now a policy improvement. And that's actually a long mystery by now, since obviously when you now want to do a policy improvement, you don't just want to do a max operator over it as you get off control. Much rather, you want to keep your policy remaining stochastic. And by remaining stochastic, that means you need to keep making mistakes in order to figure out what actually is the best policy. So it's kind of like a PhD. So in the literature, if you open the Sutton book, you will actually find two policies. And what we have by now shown is actually that they're all part of a family, which derives from a higher order principle. But the one of them basically says, with a probability of 1 minus some little subtraction, you take the optimal action. Otherwise, with the uniform probability, you take any of the others. Now that, of course, well, actually works fairly well, surprisingly well, but only if you have very few options. And it's not so goal-directed as the softmax action, which would actually now, well, basically compute an argmax as a probability, but with giving more weight to anything which has a higher future. And when you do this, you can now plug all of this in, and you can actually then replace the update of the V function with the update of the Q function, where the big difference is in the temporal difference error, because in this case, we need to plug something in for the next action, which we have never taken, which you don't even consider our problem so far, which you cannot even consider simply because it would always be correlated with the previous one. So there are two ways of how to do this. One is called Q-learning, and that's actually was by Chris Watkins, and is, I think, actually the highest cited PhD thesis of machine learning still, at least of reinforcement learning for sure, who basically said, well, just plug in the argmax for this future guy, so you make mistakes today, but tomorrow you're going to be optimal. And it works incredibly well, and again, for tabular state action representation within where you can do every state action pair infinitely often, it's guaranteed to converge to the optimal solution. The other part is called SARSA, where SARSA stands for state action reward state action. We can be quite happy they didn't use control notation. That would have been XUXU with X and U. And you simply always sample the next action and estimate then again a Q function from the exploratory policy and create on. You need to either create on policy samples or you need some crazy tricks. Now, you should realize, of course, that this all makes the policy non-stationary. We can learn fine. Now, I've told you a lot about tables. We all know tables don't work, since otherwise we could long have gone home and done optimal control. What we really need is function approximation. Now there, actually we're doing well in time, so I can actually go into the details of that. I was afraid of having to skim over it. Now there, reinforcement learning has largely focused on linear function approximation. And I should say this has quite a few reasons. One is it's the only part where we actually have any form of mild guarantees even. They don't always hold, they don't always work. Let's be quite frank on that. And we at least, if the Bellman equation has a solution, there are methods where there are converging options. So using nonlinear methods, it's like, for example, a neural network in there, you can easily show that the fixed points are not guaranteed to exist, and even worse, divergence is quite easy to show when you bring them value function methods. So you really need to be quite good at your game in order to make a nonlinear function approximator work for value function methods. But nevertheless, many of the greatest, nearly all of the greatest results of value function methods have been done with the nonlinear function. But if you're linear in the features, that's actually sound theory. You can just bring in temporal difference learning. And in this case, you want to obviously deal with the mean squared error of your Bellman, between your different value functions. So it's kind of the mean squared error of your Bellman equation. By using, now of course, the estimates twice, we do something which we call bootstrapping. And well, we of course, and here we will need, as you will see in a second, stochastic. Let's have a look into this function, and we first introduce the parameters which we actually want to optimize. Now I'll just call them omega. Okay. Then for the targets, we use the parameters of the last value function, because otherwise this guy and this guy, they are correlated, and we actually get a statistically non-sound formulation of the residual gradient. And by plugging this in, and then plugging this into stochastic gradient descent, we actually get a really simple update rule where we just have the TD error times the basis function in order to update the parameters. It actually looks fairly similar to supervised learning here. And you can plug this into SARSA, you can plug this into Q-learning. For SARSA, it actually works fairly well because SARSA usually is on policy. For Q-learning, even the smallest, even already the smallest grid worlds with the tiniest amount of function approximation can converge. So you can create three-state examples that can diverge, create three-state examples which do no longer work. So, few remarks. First, you have already realized it's not proper gradient descent, what we're doing in temporal difference learning, but it's actually something else, and we don't fully understand what something else that is, despite that most reinforcement learning people are not totally willing to do it. We completely, and this is because our value function values change after every parameter update. Now, this creates a bias, and you can even show that it won't converge to the same solution as if you were fitting the optimal solution by just supervised learning. Nevertheless, it's still useful, and you can do pretty amazing things with it. And if you really want to read up on this part, I recommend actually a paper from one of my former students. They have done pretty amazing things with this. So both in terms of Tetris, Go, TD Gammon, which in Atari games, playing backgammon at world champion level, learning multiple Atari games from raw pixel input, all of this were in the end and applications of value function methods. Now, I think we actually have the time to dive not just into value function methods, but into one special case, which is currently, I think, among value function methods, the most promising. And that is really that we try to accumulate more data and do not just immediate updates on our data, as we did with the stochastic gradient descent, but really use this to increase data efficiency. And there are only two methods in the literature which you can actually take serious on batch updates. One I will not really talk about, that's the least squares as temporal difference methods, which basically reformulate everything as one big least squares problem, just like in regression. But I will say a few words about fitted Q iteration. I should say right away, it's of course much more expensive. Now, in batch setups, we're doing something very dangerous. We probably take data from multiple policies, from the past, and we insert this all into a value function method, and we pretend we could just live with that state distribution which we have had in that data set. And it won't work with many methods. So, it won't work with many methods, and it can actually really badly diverge, which was one of the reasons why the pioneers of reinforcement learning, or value function methods of reinforcement learning, did not particularly like these approaches and didn't do them, because they simply realized that things would diverge. So two exceptions for that were actually Damien Ernst and Martin Riedmüller, who in the early 2000, around 2005, both pushed heavily for bringing these batch methods back in terms of the fitted methods. And I think for Martin, these are the main methods he now uses at DeepMind and with all of his buddies there. And for Damien Ernst, he actually uses them a lot now to optimize microgrids of the European technology. They work in actually kind of a fun way. So you would again create the targets, but you would create the targets on a batch set, then compute the optimal actions on this batch set, and then run everything through a complete regression. So it's actually fairly simple. And it is basically just a form like of value iteration. Now, why didn't people originally do it? Martin, for example, did full balancing with a full swing up there. He actually could show this in the lab to everybody who wanted to see it. It took a couple of hundred iterations, but you watched it and it worked. Completely exploratory. It was pretty amazing. And then at some point, I kept poking him, why does it work? And at some point, he then admitted, he took his neural network. Martin believed in neural networks when nobody else did. One of the guys that nobody else did. And he basically always put in one sample of his Q function at the top, where he fixed the value of the Q function exactly to 0. And that, of course, means he made sure the Q function remained grounded instead of taking off and diverging. It may not have been the true Q function because of that, but it was a very, very important trick, and this is really what made these things work. And for Martin, it was really amazing, because he used to be a professor in Osnabrück back then. Now, most of you will have never heard of Osnabrück. It's a tiny town in northern Germany, and the computer science department is actually part of the psychology department. And they didn't even have a master's course on computer science ever. So he had to actually do computer science research together with a psychologist. Didn't really know programming. And he actually wanted to win the Robo Cup. And not just once, he actually ended up winning it a series of times in different leagues, quite consistently. And normally when people win the Robo Cup, they take an army of smart students, they put them in a cellar, give them pizza and Coca-Cola, and tell them, guys, hack this up, and I want to win this cup, and you guys can come along. Usually they have an army, usually they're the big computer science department, and then they come up with a hand-coded policy, which, usually so works. And what Martin then actually did is, he had his systems learn, initially in simulations, and then later on real robots, and he could substantially outperformed. And with this one student at this tiny, poor university where you had only one PhD student, who was a psychologist in addition, with the two of them just hacking up one learning algorithm, this neurally fitted Q-learning, and making it work in all of the little subproblems they had the RoboCup, and won multiple times in both fields. I find this an outstanding success. Alrighty, you're doing still well in time. So let me sum up on value function methods. I should say value function methods came into being with Rich Sutton's PhD thesis supervised by Andy Bardo, and they immediately took off. And people were initially obsessed with them. And there's a good reason to be obsessed, because they cut out the model. They directly realized that was a good idea. But also second reason, because there were very soon these proofs by Jakola about convergence in tabular scenarios and optimal solutions. So everybody thought, oh, this will always be good. This will always converge. And with functional approximation, that will be only a small thing with hindsight. But we're going to make this work, and it's going to be fantastic. And then they started failing. And well, there was big successes like Gammon, like Checkers, at Grandmaster level, Robert Stock-Tupper, but most people started failing with many problems. Many people tried because of the fanciness of it. So why was that? Or why is this even up to today a problem? Well, one problem is you need to fill your state action space completely with samples. Now, this doesn't mean that you have to fill the complete vector space, but at least the manifold where your value function needs to live on. If you just leave out in one part of your state action space, you leave out samples, then the error in this part of the state action space will actually propagate through the whole system with complete remaining state action. So, with other words, there is a dooming analysis, again by Jakola, in this case 10, 15 years later, where he basically shows that the largest error you have in the value function over your complete manifold of states and actions will actually determine the error of the complete value function, or can determine the error of the complete value function every state and action factor. That's pretty devastating. Then you can see this as also another case of the errors of dimensionality, maybe a lighter one, because you don't need to fill the numeric space, the vector in numeric space, but it is of a high dimensional vector, but only some manifold in it. But it's still a pretty bad curse of dimensionality. And well, it can be pretty hard to control these errors, and in many cases, no really good guarantees exist, and you really need, well, you can make this work with a lot of simulation, and make this work with hell of rollouts of trials, but it's obviously not like how Rich Sutton originally believed, that this would be the way to learn fast and online under real. Now that brought people at the very end of the 90s to look again at something that looked into already in the early 90s, and that is that you could directly approximate the policy instead of trying to approximate the value function. Now, this is a huge swing back, because they had basically been dumping on the people who had suggested that. Some of them never got an academic job or didn't get tenure because of it. So it was really quite mean, and suddenly they're picking up these methods, and they're again in everybody's mouth. I should also add, in deep learning, there's still the discussion, because most of the deep mind method people live in this kind of an area, while, for example, the Berkeley gang completely lives in the policy check. But the cool part is really, when you look at how a Q function operates, you realize that whenever you're computing a better policy, a parameterized policy based on a Q function, well, you're obviously doing a large step, and you don't really know where this step is going to be. And even if values are very, very similar between two policies, well, between the Q values of two policies for different states and action pairs, well, choosing between left and right is a huge policy change. So you will actually hugely affect your value function. So with other words, that you should maybe do something which is smoother. Like, for example, a gradient directly in the policy space. Let's compare this. If we were doing a single value function, we're computing a value function by policy evaluation, and then always do, well, the policy update. The argmax will cause a large change, and our value function will also have a large change, and this gives us unstable learning. This is actually one of the two intuitions of why value function methods tend to be so bad. The second one is that sometimes simply do not. Third one. So second one is that you can't fill up the state action space, and the third one that you sometimes don't even have the stationary pointed down. Now, for the alternative for that, a policy gradient method, where a small change in the value function can actually only cause a small change in the policy, which then gives you a safer method and a more stable learning loop with a potentially much smoother policy. Now, obviously, such things have been tried forever in the simulation community. In the simulation community, people usually treat their simulator as a black box. So our complete system policy loop becomes just something where we put the policy in, and then we change the policy parameters in order to get a variation of the output. It basically means we can have a first-order Taylor approximation and can compute, in a least square sense, what is the local gradient. This works actually surprisingly well, and in the simulation literature, you can find a ton of methods for it. However, you need to usually have some tricks, like the so-called Pegasus trick of taking your random generator, and always when you're starting these modulations, you reset your random generator to the same value so that it becomes quasi-deterministic. Now, nevertheless, such an approach means that you have to probably vary your policy parameters quite frequently. And for high-dimensional policies, this can be really problematic. This brought one alternative approach, and these are the likelihood ratio policy gradient methods. And the likelihood ratio policy gradient method, well, we take now our complete reinforcement learning assumption. So we have a stochastic policy, we have the system, we have a start state distribution, and we have our rewards, where I just omitted the discount factor for the fun of which I have no clue why I don't have. And we want to really just optimize the expected return, not over a single state, not a value of a single state or of all, but over the expectation of all states. Now, I've read this on purpose over trajectories because all of the math much, much easier when you do it over the trajectories than if you do it over state action pairs. You can do it over state action pairs. Yes, I actually learned it all over state action pairs, and it took several weekends of understanding the papers. The path math, you'll see explained on one slide. But before that, I need to remind you of calculus in high school. For the Russians, maybe primary school. The derivative of a logarithm of a function with respect to, let's say, x, is 1 divided by the function times the derivative of that function. That way, you can also rewrite your derivative in terms of the function times the derivative of the logarithm. Pretty simple, right? Nevertheless, it has a name. It's called the log likelihood ratio trait. Now, we can actually do this and use this when we are computing the gradient of the expected return, where we then pull the gradient to the inside and then see, well, here is the gradient of the path distribution, and rewrite this in terms of, well, the probability, the log path distribution, and the reward. Now, you may say we haven't gained anything by that. No, you're wrong. We have gained something from it. Since this guy is an expectation, so we can actually compute the gradient only based on samples. Now, that's fairly nice, but you may directly want to complain, well, what about this guy? Don't we need a model in order to have that guy? Well, let's have a look. We want to compute the log path distribution derivative. This here was our path distribution. So let's plug the log onto it. Log turns the products into sums. You realize it's just the sum of the log policies plus a constant. With other words, the derivative is in the end completely coined by the policy. And the policy is, of course, one thing we know before we start with the whole procedure. The probability distribution we have defined in order to, which we want to optimize, which we have defined except for the policy parameters where we want to optimize. So this is fairly straightforward. We can plug this in, and it even then has a famous name. That's either the reinforced gradient or the vanilla policy gradient, depending to whom you speak. So who of you thinks this works really well? Right. You should actually be blinded at the moment, since a lot of people use it with a lot of success. For example, people around, for example, people in Berkeley have used it in quite a variety of settings, quite some success with a pretty big neural network. But actually, it doesn't work. It only works well when you very, very accurately control your exploration. So one way of making it work well is to take all the stochastic parts and fix them and choose a really good, really good policy class for your problem. But obviously, if you know a really good policy class, well, that's frequently the case for a practitioner, but it's nevertheless obviously bringing in a lot of knowledge. So no, it doesn't really work very well, but in supervised learning, we actually had a solution to that, which we could generalize to reinforcement learning quite well. And that solution is called natural gradients. And here I got to apologize, I changed these things, but apparently my PowerPoint went to crash. Well, we should say natural gradients instead. For natural gradients, what we actually do is we try not to find the gradient itself. The gradient itself is here, but we find the vector which aligns with the gradient, just constrained to the amount of damage we do to our distribution, meaning which we do to our exploration as well. This is actually quite gigantic. And you look here, you see this black, you see this is one very simple problem. It has two parameters, this policy. It's a two-state problem. It's really basic. And your current policy is here. And if you are now doing just a vanilla policy gradient, this would of course mean you look at a circle and you take the steepest direction along the circle. Now, if you do what a natural gradient does, it computes the Fisher information metric, and it computes the steepest direction along the Fisher information. And it turns out it's really simple to compute then the solution to this program by just inverting the Fisher information and multiplying it on top of the policy gradient. So there's a cool intuition with this, with the whole natural gradient and why we do this. Now, the one part is obvious for us. We want to damage the amount of change which we do to our data distribution, and henceforth do safer updates. That was what motivated me originally to get in there. But there's a cool other motivation, which is the reason why Drew Bagnall got into this at the same time. He realized that whenever you do a reparameterization, a reformulation of your policy, you will get the same answer. You get the same next policy after an optimization step with a natural gradient. Hence, it is invariant to transformations of your parameters if the policies are equally expressive. That's a very cool thing. It basically says, well, throw out the expert, plug in your favorite policy, make it work. And in fact, nearly all of the state-of-the-art methods are somehow related. So I would say actually TRPO, which is the best method which John Schulman came up with, is actually just a version of the natural policy gradient, nothing else. It's just a different estimate. And yes, they are useful. Let's have a look at two problems. One problem you already know. You take again the problem we understand, the optimal control problem, just with a linear system. Just this time we introduce a parameterized policy, which has, well, linear control policy. We know this can get optimal. We can even compute the optimal k. And we can plug in some sigma in order to have exploration. And of course, we have quadratic rewards. Now, when we plug this in and we look at the vanilla policy gradient, we see it sucks. It's really, really bad. And what does it actually do? Well, it actually runs all the way down to 0 exploration and stays there. Not a very good solution, right? Well, why does it do this? Because it doesn't know anything about the distribution it lives on, except that it gets better when it takes out exploration. So this would be the very greedy approach to life. Don't go to a restaurant, take the first dish, stay with it. Definitely not a good policy. If you look at the natural gradient, and you have again and again this amazing thing that you very frequently have all of the gradients even point to the optimal solution. You can even compute optimal learning rates at cases, so that you can do very, very large steps in policy space. And well, what you see here is then a two-state problem with from the previous slides. You see the normal gradients and the vanilla gradients, and the vanilla gradients are basically, unless you get started right about here, you will never get to the optimal policy, because everything else will bring you to one of these two local or boundary conditions. So it's really a huge change which the natural policy gradient does there, where it brings you to the optimal solution. Now, does that mean we're done? No, we're not. By far not. The methods and policy search have actually developed quite a bit, and luckily we have the time to get into them. We basically started to realize that there was a key insight in the natural policy gradient. That here we are really trying to be greedy, right? We try to exploit our life if we want to get the maximum out of it. This here bounds or regulates the amount of exploration we do in our life. So for all of you guys as scientists, this is quite natural, right? You want to explore a certain amount, but you also want to, well, get tenure or into a faculty job and a PhD and a good lunch. So you can't work for free in a wood cabin unless you're the most super driven Russian mathematician. So with other words, the data you have really makes a difference. And that was for us something which was really, really, really surprising thing when we started to look into how this appears to be the case for humans when they deal with a stochastic scenario. Now, it's a highly complicated story because humans are not always optimal in stochastic scenarios and so on, but what they very frequently do when they're optimal, that they actually try to not just match they don't just match the best actions or even some softmax of the action, but what they do is they match the reward-weighted frequencies of their past actions and outcomes. And that's really, this is totally unintuitive when you first read this, until and then you figure out that for the bandit case, Peter Dayan and Geoffrey Hinton had looked at it in the 90s and figured out that this is somewhat related to EM. And when you then realize that the reward in the bandit case would just be an improper probability distribution, where, well, when you have negative rewards, you obviously don't want to match these actions, but you really want to capture all the positive ones, except for the one case where in one state you only have a negative one, then you don't want to do something crazy far away, but you much rather want to deal with this negative one, keep. So when you look at this like a classification problem for a single day to live, it actually makes a lot of sense. And it brought us then to derive a series of algorithms which where we just reformulated everything as an EM-like algorithm, where the reward was used as an improper probability distribution. And what we're really replacing then is the log likelihood by the log expected return. And this would give us, well, always a tight lower bound, we take a jump to the next policy until we finally converge these two local updates. And you recognize, of course, this here is again the log over the path distribution. So all the math we've seen already for the policy gradients, we can also use in the greedy update step. So we can do a safe greedy update step so that we can do larger steps in the policy space, assuming we are not at a plateau where this method obviously fails drastically. If you're at a plateau, well, your lower bound will never reach very far. In fact, you can derive both policy gradients from this lower bound by simply, well, saying that the two policies are close together, and then you get many little steps, and just like before. Or you can do the argmax on the lower bound, where whenever you have a good lower bound, well, in that case, you do quite well. Now let me show you one video which back then when we came up with this is fairly fancy. We initialized the robot by imitation learning approach. We show it, this is how you do a ball in a cup movement. The robot reproduces this scenario, and it obviously fails. Why does it fail? Well, A, it has no hand-eye coordination. B, and more importantly so, our robot has a 2-kilogram wrist. Imagine if I was giving you 2-kilogram weight to your hand and you would have to do ball in a cup. Most likely you couldn't do it. The human instead has a very light arm with muscles. And muscles are, for us roboticists, they're a wonderful actuator. We would love to have them because they give us really high accelerations. They have lots of inherent beautiful properties. We just don't have them. But Peter hopefully will give them to us at some point. Audience. You may have seen a robot, but that was, I don't know. So we need to keep improving instead by reinforcement learning. And for that, always slightly modify our actions. And this modifying the actions is actually so small, it's a little tremor. Pretty much like a human tremor when you're first getting into a new car and you're steering, these little tiny movements which you make subconsciously is due to the noise in your actuators. Actually the same noise which we're using here, just in artificial way. And we're actually using the noise of the teacher even to initialize the policy. It gets better and better after pretty much every trial. After about 40-something trials, it gets the ball into the cup for the first time. After about 90 trials, you can show it reliably in the lab, as we've done at past summer schools, so that it doesn't fail a single time for a whole afternoon. And now how does this compare to humans? Well, my former PhD student Jens Kober has a pretty large family, and he did an experiment on them. Now that's obviously a very biased one, you could never publish that. But among his cousins, we know that the 6 to 8-year-olds don't manage to learn it at all. The 10 to 12-year-olds learn it within 30 trials, so they're slightly faster than our robot. And the grown-ups learn it within 3-4 trials. So it seems to be only me who took 3 months to learn it. I should add, for the robot, we still use numeric rewards. For the cousins, we use chocolate, which is a stronger incentive. Jens family had some of them were circus members in previous generations. Maybe there's some genetic predisposition. And unlike the cousins, so we looked at the videos of the cousins. Unlike the cousins, our robot never cheated. So let me bring you to the key problems still, which I think in reinforcement learning we are now in policy research in particular, but I think in all of reinforcement learning we are just really starting to understand, which are when we really solve them, probably the ones which give us all the leverage which we need in order to get to pull through and get to really a new quality level of reinforcement learning. Now I'll show you the first glimpse which we have onto this and been working on for the last couple of months. The first thing is that we really need a notion of data in the generic formulation. To some extent, that's done by the EM-like methods. But the EM-like methods are somewhat unnatural still. Your reward is suddenly a probability distribution. How can that be? Doesn't make sense, even as an improper probability distribution. Then the optimization bias, that whenever you're bringing in a model, and at some point you want to bring in models, since all models are wrong, but some are useful, well, you really want to be able to deal with it. And then finally, well, features have actually been fairly artificial, right? You just said, oh, we are just going to approximate these value functions. What does this actually mean, approximating a value function? How did these features get into this instead of being a table? This is actually a pretty long chain of logic, and with the many bugs which I explained to you earlier, so it's actually not at all that straightforward. Now, the first one actually has an insight from the natural gradient, and that is that you want to stay close to your data distribution Q. And the second part, you can probably deal with it by saying that just like in the natural gradient, well, you really want to bound the information loss between the state action pairs which you've seen so far and the ones you're generating. And finally, well, you can bring in the features by basically saying we do not want to represent the dynamics anymore. So these here would be distributions of states pulled through a policy and then subsequently a model. But you don't just do the dynamics, but you just look at stationary feature averages. Now for us, this brought a method called relative entropy policy search. There are many generalizations of it. They really would take the general reinforcement learning problem, which is equivalent to optimal control, or from which you could also derive the value function as a tool, and you bring in the features, you bring in this additional constraint, and when you plug this in, you automatically get a closed form solution for an optimal policy, which is somewhat related to the Gibbs policy. And except for this Q, which points where you have data, it actually is like a Gibbs policy because the TP error, or the expected TP error, is actually the same except for a constant offset on the position on X, so that you can actually cancel it out in the fraction. But what's even cooler, you get a lock-sum optimization program, which is guaranteed to give you a good value function. And these are all direct results from this previous year's problem, and have actually opened a big new path, a big new alley for us, as of how to do reinforcement learning and how to actually safely learn even a model, use the model within a policy search method without having to fear that any crazy actions resulting from your model will destroy your system. So with that, I'm ending also the policy search part. I hope to have made clear we have this third alternative. Policy gradients have really been the dominant method here for a very long time, and still are for people who do policy search on deep neural networks, for example. In many ways, exploration is still an open problem, since even for the relative entropy policy search, we have to set somehow this epsilon, which in the end also points how fast we can go. And well, for us, perhaps is kind of the method of choice. You can show that it's a generalization of both natural gradients and pure PO, and well, it works quite well in practice. So with that, I would like to end, and I hope you've seen there's more than just getting a model out of data. In many cases, you want to get a value function and a policy, but at least you may want to get your policy out of your data. And wouldn't it be nice if you couldn't replace Donald Trump by a good optimal policy? Well, let's hope for that, and I'm happy to take questions now, and I'm even on time. That's directly before lunch. Yes.
Just a small technical thing. some slide when you define the reward function,
Mm-hmm.
define it as a function of state and action.
Yes.
And I've seen it always. They're sure defined as a function of state and action of the end state. So does
Next
that
state,
carry
yes.
any does that carry any implications when you reduce definition or
it introduce you basically when you bring the next state into the reward function, then you have an additional source of noise. Now many people introduce it first and then take it out by writing the expectation then, in which case it's lost again, so it was for nothing. But in some cases it could actually be useful. For example, if you don't want to make your system too coy about getting a reward but in a particular state action pair, then it makes a lot of sense to give it a nice priming towards this other state. So for practical purposes, it can be a very smart thing to do. From a theoretical point of view, it doesn't make much of a difference, at least if you have a good model.
So I was wondering how well these methods work when you have very large action spaces. So how does how successful are these methods, and what would you recommend if very large action space?
Ooh, that's a good question. So personally, I usually deal with the continuous action spaces. They're usually too large to ever be searched. Where you would actually do a local search maximal at best. In which case, obviously, a policy gradient method is much more helpful because you have to deal with way fewer actions. Where I think it really depends already which road you've taken, though. If you deal with many actions in a discrete scenario and you have, let's say, a really good model of your system, and you do optimal control, then having many actions may be a good reason for you to not use value iteration, the algorithm I explained in depth, to use policy iteration, where you always do the policy evaluation step and you will only evaluate few of the actions, only the ones which have a lot of probability, and henceforth you need to look at way fewer actions. And surprising thing in the policy iteration loop is, well, you have to now create these complete lives for evaluation. You would initially think that this would be way more expensive than value iteration. You'd have to live multiple lives instead of just one. But the max operator, if you have very large action spaces, is so much more expensive that it's more than 10 times more expensive quite quickly. And it turns out that if you do policy iteration, do this well with the max operator, you can converge within really tens of iterations. And that's actually one of the complete mysteries again, and which we know is a mystery since the 1950s. And people like Benjamin Conroy have spent a lot of time on figuring this out, but I don't think there is a true answer to that. But that would be two answers I would have for value functions. Maybe for pure value function methods, I wouldn't know what's best. That's probably, well, if you're on policy, something like SARSA is definitely better than learning in that case because of avoiding the max operator. But except for that, really give you more answers there. But do policy search. Oh, never mind. Okay.
Hello. So I have two questions, short questions, which are kind of interrelated.
Mm-hmm.
The first one is, seems you need too many trials to actually start learning anything useful in general in reinforcement learning. Are there any ideas to reduce data complexity of these algorithms? And the second one is, are there any visible ways of reducing the variance in the gradient you estimate when you're doing some of these gradient-based methods? Because if you have lots of fluctuation in the gradient, you're not going to learn anything useful in finite time. So are there any ways to learn fast, as humans, for example?
Okay. So first, the part about being fast. Now, obviously, for us, fast is when we can learn something like ball in a cup in less than 100 trials. That's actually quite fast, given that you don't have your complete life of learning hand-eye coordination part. So I just want to put a little bit of a dampening on the fast. In reinforcement learning, of course, we have pretty much everything. We have people who do simulations and do billions of trials, and then learn in billions of trials what a human can learn in 50 trials. But the question is how the human got to that. Does the human do mental rehearsal when the human sleeps, and by that actually pre-trains the policy? Or are we actually so pre-engineered that our policy parameterization fits perfectly to the tasks we encounter? Like the stabilizing controller, which we learn when we get born, which is built basically in for walking, generalizes directly to bicycling so quickly because it's the same policy we're using. So there's a lot of answers to that. Generically, when you want to be fast, you want to have a model. You want to make the method work safely with the model. That basically, I think, means on the long run that we need to bridge between policy search and model-based reinforcement learning, which currently does not exist at this point. But that's a hunch. That's not something I can tell you a model helps. I can tell you policy search helps. Staying close to data helps for getting faster. I can tell you that value functions are usually quite slow despite of their theoretically great properties. I think these are the key things I can give about the first question. Now the second question is about variance in policy gradient estimates. Now it's basically it was a science by itself for quite a while. So the first thing we realized, and see whether I can pull up a slide from one of my classes for that. Generically, we can also in policy search, obviously, can rewrite the policy gradient theorem in state action formulation. And already by then going from trajectory to state action, and using the Q function, we can reduce variance. Then by finding optimal baselines, so you can actually subtract an arbitrary function here without biasing your gradient, you can again reduce the amount of variance. And then there was something pretty amazing when policy gradient methods reemerged. That's the so-called compatible function approximation, where we realized that some projection of the Q function, so it's not the true Q function, unfortunately, it's actually the advantage function, as we know by today, can be composed, so basically the non-state-based part, can be composed actually based on the policy. That's a very, I don't know, I would call it a fascinating insight, because it literally means that that we always know, at least for part of the value function, the right kind of function approximator if you want to approximate. And that again introduced substantially the variance. And it turns out, and that's why people, well, then we figured out one more thing, and that is that you could actually compute this inner integral analytically, which we did in the all action metrics, and which is actually one of the key tricks in TRPO of John Schulman, that you do not explicitly take all actions, but you actually bring in a generalizing term. And well, then obviously the natural gradient all blew this away, because the natural gradient, and you could show that the parameters of this compatible function approximation are actually the natural gradient. And so it suddenly felt like something useless to do baselines, hints, and all of these other things, and instead you wanted to directly use the natural gradient instead of first computing this compatible Q function, plugging it into the vanilla policy gradient, and then making everything work. But yeah, there are the optimal baselines. There have been 10, 15 papers on that past. If you ping me, I can send you a survey on policy gradient methods, which is still up to date, I think.
So in the beginning, you identified as the main problem for model machine learning that was essentially specified and see this is good. Is any other potential problems with machine learning? Which scan?
So this is a problem of model-based that that model has problem.
Yeah.
Model-free obviously has the problem that we make bad use of our data, right? If I want to be, well, if I'm model-free, then I'm not really making very good use of my data. If I've seen something very rarely, I really want to be model-based. But on the other hand, I need to make sure that I stay close to this data and not end up in the regions of invalidity of the model. And for model, what are shortcomings of model 3? Generically, well, you never have enough data, you never want to interact much with the system, and we're obviously much slower than we could theoretically be the really, really good model. But again, finding a really good model and making reinforcement learning work safely with it is very hard, and that's the reason why most people don't use models. Now, I still think that the bridge needs to be that we really use the data we have generated so far, on which the model is based, as a regularizer on our policies. Whether that is the way we of bounding the KL between the state action distribution as it, whether alrighty, could have only failed again. Whether it needs to be should be the KL as we did, which case you could bring in the model then in addition. But that's the right way, I don't know. We're actually working on a complete family of methods there by now, falling out of other divergences. And it turns out that pretty much all of the known policies is together with compatible critics of totally different forms can be derived from first order principles. But you have to keep our fingers crossed for NIPS and tell you more.
So it sounds that if you had a model that was giving more robust predictions and perhaps quantifying uncertainty, that would go a long way to
Absolutely.
Policy.
Absolutely. I mean, the approaches, for example, of Mark Deisenroth around Tuco, which he worked on a couple of years ago, that was, for example, in that sense, a really nice step into this direction. But unfortunately, it always only worked along trajectories in finding and did scale very well. But basically finding the methods that really directly incorporate the uncertainty about your model estimates, not just your predictions. I think it's the generic key to make models work.
So we are already over time. So sorry for those whose question we can't take. So I would suggest that those still have questions, just take Jan for lunch because lunch is already waiting. Let's thank Jan for his great introduction.